So let's now take a look at functions of three variables rather than just two. And a function of three variables maps subsets of R3, the 3D space, to R. And of course, you don't need to map all of the 3D space to the real line. You could choose any subset of the 3D space. We could also give this in terms of explicit representation, much the same way that we did with functions of two variable. So we feed the function three values, x, y, and z, and it returns a number. That number can be associated with the w axis, okay? A fourth axis, a w axis, okay? So let's take a concrete example of a function of three variables. So here you have the function given by this expression of x, y, and z. So what do you do when you get an x, y, and z value? You plug them into here, okay? And we could just take a quick example here. Let's just take f of 1 minus 1 and say 1 there, and that would be 4 minus 1 squared, that's our x, minus negative 1 squared, that one was our y, minus 1 squared, and we get square root of 4 minus 3, or 1, okay? And notice here that if x and y or z were too high, then I would get a negative number in the square root. We can't have that. We can't have a negative number in the square root because we're only dealing with real functions. So we need that the argument inside the square root is 0 or positive, so that it's greater than or equal to 0. And that translates to x, y, and z having to respect the relation you see here. So our domain is the set of points that respect that relation. Well, now what respects that relation? Well, x squared plus y squared plus z squared equals 4 is a sphere of radius 2, but we have a less than or equal to there. So everything even within that sphere, so you have a ball of radius 2. Okay, anything within that sphere also respects this relation. So you get this entire ball, solid ball, getting mapped to the w-axis. And for example, taking the point 1 minus 1, 1, which is some point up here, say that point up here gets mapped to the point 1 over here, okay? Now, think about the graph of such a function, how it should look. Well, the graph is going to be x, y, and z with a fourth axis, okay? You can't map that. We cannot visualize 4D space, spatially, right? That's not going to work. We can't get a w-axis pointing out over here and visualize that. That w-axis would still exist in our visual 3D space, okay? So what are some strategies then of representing this w-axis, okay? So imagine we go to a point, instead of trying to think about some a visual axis, we could agree that the higher the value of that point, the more red it's going to be on the spectrum, okay? Or say the more blue. And we could use a color spectrum, Roy G. Biv. If we agree that the redder means higher value, or vice versa, maybe the bluer means higher value, however you want to represent that. So you could represent a function of three variables in terms of color, like a sort of temperature plot. But please do keep in mind that this is not the function, this is the domain. The value of the function for different points in the domain is on this w-axis, and we need some kind of ingenious trick to represent that, since we cannot spatially view 4 dimensions. So for example, what you see here is the domain of, so that object there is the domain. Where is the graph? How does the graph look? It's represented by the color, okay? So the redder The point is, the higher it is in the range. Okay, so say something very red might correspond to W equals 7. Okay, where something very blue might correspond to W equals negative 3 or something like that. Okay, so that's the best. That's one way to represent functions of three variables. We could also represent them using level surfaces, which we'll talk about.